You are welcome to Module 2, Unit 5 of Physics 115. This unit explains motion in 2 and 3 dimensions. We are going to extend the motion treated under one-dimensional space to 2 or 3 dimensions, and many of the ideas used previously in the Unit 1, 2, 3, and 4, such as position, velocity, and acceleration, are used here also, but in a little more complex because of the extra dimensions. Having watched this video, you should be able to define 2-dimensional motion, define 3-dimensional motion, then solve simple problems in motion involving 2 and 3 dimensions. A 2-dimensional motion is defined as which has 2 components, x component and y component. A 3-dimensional motion is defined as a motion which can be described by 3 components, that is x, y, and z. Position and displacement. In order to locate a particle, one needs to find the position vector, which is a vector that extends from a reference point to another point. In a unit vector notation, it can be written as which is equal to x plus y j plus z k, where x, y, and z are components and I, j, k are unit vector. As particle moves, its position vector changes. If the position vector changes, say for example from r1 to r2 during certain time interval, then the particle's displacement during the time interval is written as delta r equal to r2 minus r1. Using the unit vector notation, then we can write that delta r, which is equal to s2i plus y2 j plus z2 k minus x1 I plus y1 j plus z1 k, which is equal to delta x I plus delta y j plus delta z k. So let us look at this example number 1. The position vector for a particle was initially given, and later as that what is the particle's displacement from r1 to r2. So let us look at solution for that. We have delta r, which is equal to changing delta x I plus delta y j plus delta z k. So using this, we should have delta r equal to 9 3.0 minus 3.0, close the bracket, then the unit vector plus open bracket 2.0 minus j, then plus open bracket 8.0 minus 5.0 k. This gives us 12 in meter I plus 0 in meter j plus 3.0 in meter k, which is finally written as just 12 meter, of course the unit vector must be there, plus 3.0 meter k. So let us look at the average velocity. Also, the average velocity can be written as, so the average velocity is written as v avg is equal to displacement upon the time interval. Then from what we have done earlier, we can simply write delta r upon delta t, which is the same thing as delta xi plus delta yj plus delta z k, everything upon delta t. Then this can be split into delta I upon delta t plus delta y j upon delta t, then plus delta z k upon delta t. Let's look at example 2. The position of a particle moving on an x-axis is given by that, where x is in meter and t is in second. What is the velocity at t is equal to 3.5 seconds? That is simple enough to solve. So let's look at the solution. So we know that velocity is equal to change in displacement over change in time, which is written as d upon dt, then 7.8 plus 9.2 t minus 2.1 t cube. So if we carry out that differentiation, then that gives us, if we differentiate 7.8, it gives us 0, because differentiation of a constant gives 0, plus if we differentiate 9.2t, it gives us 9.2, then minus, if we differentiate 2.1 t cube, it gives us 3 times 2.1 t square, which is written as 9.2 minus, 3 times 2.1, that gives us 6.3 t square. Now at t equal to 3.5 seconds, then we just substitute the value of t into v. So v becomes 9.2 minus 6.3 times 3.5 square. Then we have 9.2 minus 6.3 times 3.5 times 3.5, which gives minus 68 meter per second. So let us look at average acceleration. When the particle's velocity changes from v1 to v2 in time interval, then its average acceleration during this time becomes avg, which is equal to change in velocity upon change in time. So let's look at example number 3. A particle's position on the x-axis is given by that with x in meter and t in seconds. What is the particle's velocity? And b, what is the particle's acceleration? That we can follow the same example that we have done earlier. All we need to do is just to differentiate the velocity that we have for the second time. We have so let's look at solution of that. We have a using a equal to change in velocity upon change in time, but we know that v equal to change in displacement upon change in time. So we can first differentiate our position such that dx upon dt is equal to dt of 4 minus 27 t then plus 3 cube. So that gives us minus 27 plus 3t square. Then acceleration is now equal to dv upon dt, which is the same thing as d2 dt square of 4 minus 27t plus t cube. Okay, and that gives us d dt of minus 27 plus 3t square. And if we carry out that differentiation, like I said earlier, differentiation of a constant is always 0, so we have 0 here plus 2 times 3t, okay, which gives us 6. That is the end of the unit 5 of that module 2. So at the end of this video, you've seen we have seen how to find the velocity from the particle's displacement and how to find our acceleration from the particle's velocity. Of course, in the next unit, we are still going to employ this process and this procedure. Thank you.